Okay, let's go ahead and get started. So I changed the schedule. I've been trying to adapt to the time changes and everything. So just a quick note. I'll be starting at 9, going forward from 9 to 10, and I'm going to take it down to just an hour instead of 90 minutes so that we can get to the point, get something done, and kind of stay focused and kind of have this be hopefully a focal point for your day, something you can just come in and do and just know that you're not going to get overwhelmed with time. This also is, an hour is not too hard to push to YouTube every day. So hopefully everybody could check in every day for that hour if they want to. That's too much to make up. So that's the new plan. 9 p.m. every night, my time, 9 to 10, really quick. It also means that we're going to have to get right to the point faster than we do. We won't be able to meander around as much. I'll save that for co-working or other things, other times during the day. So what does that mean for us? Well, the first thing we need to do is open up the PDF for Head for C. We are still in Chapter 2. Well, we made a lot of mistakes last time. So I think it was Section 8. There was some significant errors that we made that we kind of caught wind of at the end of it when somebody raised the issue and said, hey, you know what? The way the book is explaining arrays is the same as this other document, and I posted the document there. Are we absolutely sure that this is wrong and that the standard says that we can't define arrays? And so let me recap. I really think it's important that we go through this because we went to great lengths. VMT was the one who initially reported that this was not correct, and then come back and did extensive research and said, no, actually I was wrong, and learned something, which is interesting because he's a veteran. So for him to say that is I really appreciate that. And we discovered something. So it turns out that the book is right, which is actually really good news. And what do I mean by that? So if we go back into the, I think it was the Monty project that we were kind of getting sidetracked on. If you'll remember, we were going through this and we were trying to notice, the difference between a character array and this, if they were the same. This is not true. This is prohibited by cert rule. That is a lie. That is not true. And we've got that confirmed at this point. This is not the same thing at all. That continues to be true. But these two are identical. They're literally identical to each other. And so this one, I think, doesn't create the same copy, but they're effectively the same. These two are effectively the same as far as you are concerned. What does that mean? So we went to a great lengths to say why you needed to put the double constant in here to make a constant. This stuff here is absolutely irrelevant and wrong. And so if you watched session 8, I'm sorry, I'm going to leave it there, but I allowed myself to be influenced by the people in the community who are more knowledgeable in C coding than I, and the book has been wrong on a couple of occasions. So, and they discovered that. Well, they are the ones who went looking further to figure this out. And so this says, do not attempt to modify string literals. But this is a completely different issue. So we're going to go with what the book says, and we're going to stick with that because we now have it as we have a university computer science text that says the same thing, and we have this book saying the same thing. And there may be people out there that disagree slightly, but these other things are not as relevant. You could use a character array or not. So what I'm trying to say, and let me recap. So very specifically, using a pointer like this doesn't work. It never did, and that was never the question. What the question was is whether or not doing it the right way, as they call it, by using a character array notation, not array, but the array identifier notation. If this was right, and this is true, in fact, this has been confirmed now at length. When you do this, this is the constant, but what gets put into the identifier, this is an address that's pointing to something on the stack, which can safely be changed, which means the Monty program is completely valid. It's not invalid. And, that makes me trust the book even more. I'm really glad that we found that out. So that is where we're going to go with this. And I'm gonna recap on this stuff right here, because I don't want anybody to be confused, even though it's going to take a bit longer. I feel like it's a good use of our time, and we'll continue to do the Monty project. We'll go back and type in the Monty project as we did initially, and see what's up with that. Now, this project has us doing this, so let's go back. We're gonna do this fast because I do want to make more progress. But this program is not right. This program is broken. So let's actually go ahead, and we're going to put wrong here. All right. So how's it going, Jim? Welcome. So any of the individual array string values are using a string literal instead, it will falsely appear to allow the same thing. They actually do not falsely appear. They are the same thing. And so all of those concerns previously were unfounded. Okay, so these two things are the same, but what's not the same is this, right? And that's all I'm going to say about that. What's it? So there's one thing you need to make sure you understand if you're getting into this decoding stuff. What is the difference between these three things? They can all sort of be used in the same way, but not really, right? And let's take a look at that. So how are all three of these things similar or different? And that's something we learned in the previous lessons, and we've been reading here. So let's try all three and see if let's write the program, let's write the rest of the program, and let's try each one and see what happens differently. Okay, that's what they want us to do in the book. So let's stick with the book. So we're going to go ahead and make this hey Jog, we're going to go ahead and make this JQK thing. We'll get rid of the ace there. There's not that. And this is supposed to be an O. We need that if we're going to have those be identical. Okay. So we're going to try all three of these. Let's first try this one as is in the book. So again, if you're following in the book for this section, it's correct. You can just read it and go with it. So let's do the pointer. So we did the pointer one. That's what this is. And they're all pointers, but this is a special pointer, right? This is not a character array pointer. This is just a plain old pointer. And know if you know the difference, right? One of them comes with kind of a built-in knowledge of how big the thing is, the size of works, if it's in the same local context. If it's not, however, remember pointer decay. So then we have this. What does that say? Well, let's do it. So this is saying I want to make the contents of a card be cards 2. So 0, 1, 2. So that should be the king, right? So let's go ahead and put that in there. So char a card equals cards 2. All right. And let's just stay with that. Let's not do all of the swapping around of cards right now, because we kind of want to keep things clear and just get right to it. And then let's do let's do some debugging. So let's say printf cards. Let's do cards, shall we? Main println lol. So we're gonna do cards here. We're gonna do a. Well, I mean, we could just do put s, I guess. A card. A surprise stream. Yeah, I talked about the time changes. Time change from 9 to 10. We're gonna make it an hour, so that I have time to eat and get recovered. My wife doesn't get home till later, so from now on we're gonna do all the streams at 9 o'clock. That's gonna be at least through 2022, because because that's her work schedule, and she's just not home in time for me to do it earlier than that. And I'm not giving up having dinner with my family to teach y'all. Just not doing it. So it's bad enough. So let's do this. So here I have the card. Let's go ahead and see what that does. Anybody want to predict what this is going to do? Right now, take a moment to predict what you think this is going to do. I think it's going to print out K. Because 2, remember, the index starts at 0. So 0, 1, 2. Right? And I don't think this is going to crash. I think this is going to have to work. So here we go. We're going to do make, oh, look at that. Expects a constant. It says, note, expecting constant, but argument is of type char. Interesting. Argument is of type char. So why isn't that working? I think you know why. Just to teach the internet, yes. So it didn't work. It didn't work. Why? Because it couldn't realize what it was. A card is a single character, and putS works for strings. Let's try printf. Let's say printf. We'll say now I have one character. I think that's the thing. I don't remember. I think it is. And we'll say a card. Let's see if we can get that to work. Make. Nice. Some money. Yay, it's a K. Okay. Yep. Thank you, Jura. 25K. So good job. We got it. All right. So what we expected is true. Now let's immediately have fun with this and jump ahead in the book. And let's go do this assignment. The first thing I'm going to do, this isn't in the exercise. I want to change the value of K. So let's say I wanted to change the value of K to something else. We could say, let's say I want to change cards 2, which we know is a K, to be a lowercase k. Okay? And what is that going to do? Is that going to work? Let's see. And let's say, let's actually do the whole assignment all over again. How about that? Let's see what happens. Let's see if this works. I love blowing stuff up. Oh, blew something up. Oh, you know why? Because we defined it twice. So we have to remove the definition. But we can probably reuse it because it doesn't say that it can't be changed. Yep. So let's change that. Let's run that. So, oh boy. That doesn't look good, does it? And that is the error that's discussed in the thing. Why did we get an error this time? We got an error because you cannot change the value of a character array when it is a pointer. And this gets back to the book that I'm kind of jumping ahead, but this is where they say, boom, bam, bam, hey, it doesn't work, right? And it talks about why the strings can't be updated. The string, it can't be updated. And let's talk about why. So these two are different. So when you put a star in front of it, you do it this way, you cannot modify the values of the string at all. And the pointer in this case, and this is kind of cool, the pointer in this case is pointing to the string literal in the constant section of the stack and not the heap where it can be changed. If you change it to this, then the difference is this becomes an array, a copy of the thing, the constant, that is pointing to the copy and not to the constant. I think that's the clearest I can say it. And that I'm really glad we went through all this hassle because this is very definitively the way this works. We've now thoroughly found out that was the problem. The people who had problems with that statement have rescinded their problems with it. They've said that they were incorrect. And then we found an additional source that this is how C works. So the difference is this pointer, they're both pointers. Cards contains a pointer, not cards in this case contains a pointer, and cards, the identifier, contains a pointer as well. Both of them are pointers. The difference is this pointer is pointing to a constant that is in unchangeable area of memory and gives us a segfault. This pointer is pointing to a copy of what was in the constant that is in the heap. So it makes it's more space, but it allows us to change it. So if you don't need to change your string ever, this is the way you should do it, and this is the way most people do it. Most people will write it that way. Most people will probably put a constant in front of there as well so that they don't accidentally do what we just did, because that would force it. So if we wanted to do this properly, right, what we could do is this. We could say, I could say a const, right? And this is where the advice was coming from people before. This says, hey, cards is constant, and not only that, it's been declared that way, so people reading the code won't get confused. And most people aren't. But if you do that, then you do this, and it's not going to do it. Now the error is caught when you're making the program, when you're compiling the program, and not left acceptable. So if we don't do that, right? Let's go back to the other version. If we don't do that, then what? It'll happily do it. Whoops. Or does it? Maybe it doesn't do it. I take it back. Oh, this one. Yeah, never mind. Watch. This should compile. Yeah. This compiles. Even with all the warnings on, this compiles. And that's bad. And I think that's what tripped up some of our veterans. Our veterans are so used to not doing this and putting the constant there that this is a bad practice. I agree with them. They're not here now, but I agree with what they were telling us to do with the constant, because why? And even though the book doesn't say to do this, putting the constant in your declaration is an extra cue to you, the coders after you, and to the compiler that this shall not be changed. You cannot change this thing. Even though you couldn't change it anyway, that gives you that additional check while it's compiling, instead of blowing the fuck up when you run it like this, which is, .monty. Okay? This is way worse. All right? So I appreciate all the help everyone's been doing, helping us out with, but I personally think that one we know blows up. This one we know doesn't blow up. This one, it blows up, but it blows up when it's trying to compile. It won't even compile because it's incorrect. I was like, no, I'm sorry. You can't assign to a constant. I told you can't do that already. Now, why that isn't thrown earlier on with this kind of stuff at runtime is probably because of all the stuff everyone's been talking about with, evolving standards and everything. And that's probably why this version up here is even allowed to compile at all, but it's a gotcha. So we're going to put the constant there. Right. Now, that right there won't compile. So let's actually put this. Let's say compiles, but boom. Right. This one is won't compile. Okay. I'm going to put wrong. How much time? How much space we got? Okay. Wrong. We have this one is wrong. And at least not in this. We're going to finish out the thing here, right? In this usage, it's not going to work. So we know that's a boom. Let's take back our other. So now we have. So then we have this. All right. Now let's do the other one first. Okay. I like this version. I still like this version better. This was what got me going down. I like this. I do. I really like this version better than the other ones because you're never using it as a string. Right? So this is not a string. This is an array of characters. and it does not have a null because of the string. All right. And let's try that. Let's see that if this blows up. This will actually work just fine. It should work just fine. Monty, run Monty, and we get K and a lowercase k, and it changed it just fine. No problems at all. Now, that's all well and good until we add the other part of the exercise, which has us add this, where you're putting S-ing the whole card, right? Where you're put S-ing the cards. Now this is probably a seg fault, I'm guessing. So let's see. So let's say this. I'm going to say it's wrong-ish. It's kind of okay, but it's not a string. So if down here, if we did put S, right? Put S cards, which is a part of the exercise. What's it going to do? Well, it actually will work. Or does it? It doesn't, right? This is also wrong. And I'm going to put cuz put S. Right. Because there's no null value. So if I put a null on there, though, that's totally valid. But I want to see the cases where this is a blow up situation. So let's do that again. So there's no null there. Let's put a right version. What else is going to seg fault? Okay, so that's also wrong. We just proved it. Now, this, however, is fine. This is fine. And that's kind of where I was going with this. So this is fine. Let's see. Let's prove it. So we're gonna make it and then run it. All right. So there we go. We see there's no problem there. Did exactly what we wanted. That's the first version to not blow up. All right. And then the next version to not blow up is going to be this version. Right? And this is exactly the same. Right? So the difference between this version and this version is that this version never puts a constant in the constants space. And I'm really glad that I understand that finally. When you do an array like this, there's not a duplicate created. It creates an array, and because it's not a string literal, it's not created in the constants space. And I wish I could show that. Find verbose, no copy. So I'm putting no copy there because why? Because the only time a copy occurs is if you're using a string literal. That means you're having double quotes, and inside of the double quotes are, the letters that you're using. This is a string literal. And this injects slash this, injects a null at the end, puts all of that into the read-only section of memory, and then creates an empty copy of that. So if you're concerned with memory, I mean, I don't know if you are, but if you're concerned with memory, this nice way of writing it, I believe, takes way more memory than this. Because this one, I'm almost sure, we should probably test it, does not create a copy in the constant space. This allocates an array on the heap, and then puts that content into the array on the heap. But because we're using this special string literal notation here, this string literal gets written exactly as it is into the constant space of the memory, and then a copy is implicitly made in the heap, and that a pointer to that one is done here. So it's like the same as doing both, except for at the end of this one, you end up with a constant still in your constant memory area. Not a problem, it's just different. So, and that's super important to know, and I'm really glad. I feel like I'm getting my head around that one. And this is let's see. This is fine. Copies, stringlet, copies is string literal. So those are notes to me so that I can know the difference about what C is doing along the way. And I like to know those things. Exact same in assembly. I think you probably have to mess with the optimizations to see that. Are you telling me that this about the constants and copy onto the stack? Did I say stack instead of heap? I'm so sorry. As if you weren't confused enough. I may have done that. I mix up the stack and heap all the time. It is the stack. Okay, sorry. Sorry, I mix up the stack and the heap all the time. It's still stack. Yeah. I'll try out the options. What we want to make sure is if I'm a liar here, right? Heap equals malloc. Okay, nice. Heap is malloc. Stack is everything else. Okay, so that's good to know. I did not know that. So I mean, I know it's taking us a long time to get through this, but I really appreciate this. I really love it that we're going through it so meticulously, because knowing C is pretty much useless unless you know what's happening under the hood, in my opinion, because C is supposed to be closer to the metal, like assembly. And so if you want to, lots of other languages, I don't give a shit what's happening underneath, other than how much RAM is it using? Is it going to blow up RAM and disk and CPU? Period. Garbage collection, I don't give a crap. I really don't. If it's going to do garbage collection, as long as it's going to interfere with my performance because it's like some really high performance kind of thing, then I don't care. I don't want to care what's happening underneath the hood. But with C, I really do. Because most of the times you're going to be reaching for C as the right language for the job. You're going to be doing it because you have access to the stuff underneath, and what it's doing to the memory underneath and the performance and those kind of things actually matters. You're writing system drivers, you're writing kernel code, you're writing, low-level network protocols. You're doing, things with system calls. The stuff where people reach for C and will continue forever to reach for C are the kinds of applications where understanding exactly what the heap, the stack, the constants in that section are is a big deal. And so I'm kind of being pedantic here because I want to truly understand that, and this is kind of a precursor to me diving into assembly eventually on my own, so I can see how assembly is actually doing things, and then see how C is saving us from some of the hassle of writing that out, and ultimately better understanding languages like Rust. Once you understand those things, if you choose to dive into Rust, just today I heard about Rust being used to create Python stubbed modules so that you could, kind of like TensorFlow has done with C++ or C, and then you use Python. It's nice and easy to use it, but you're getting all the speed advantage of that. And that's actually a pretty nice killer app space for Rust. I don't particularly like the language or the community, but that's a killer app space for Rust. And I can understand Rust better by understanding how C handles things underneath as well. So that when people say it's unsafe, if you're a beginner, you have no idea what that means. And in order to understand what it means, you need to dig underneath what the language is doing. And as soon as you get to Rust and C, you're starting to dig underneath. Now, to be fair, languages like Go is like right between there and Python, which is like way up high, right? And in the case for Go, it takes more of a, I don't really care what's happening under the hood. You can get there and dig under if you want to, but if you really just want to live in user land and la-la land, you can. And that's why Go is so valuable as the cloud native, go-to applications language today, and that's why people don't pick Rust for that. Rust, however, gives you more granularity when it comes down to the lower levels, and I think it kind of expects you to understand those things. It covers up that complexity in a different way. Bottom line. So yeah, even changing options still shows the exact same assembly for using a character array with or without a null terminator. To me, that implies that that you're telling me that it makes a copy. It's the same assembly. I don't know. We know that this. I'm just going to put verbose here because I don't know. C and C++. Well, all of the artificial language intelligence languages are C++. They're written in C++. They're just covered over. They're covered over with other languages to make them more able to do, you know, darknet for C. All right, so let's go back to our exercise. I promise we'll get through this fast here. So all they're doing here is they're just confusing you. They're just shell gaming this stuff up. I really don't care about this, but I'm going to go ahead and put it in here anyway. So they have 2 equals 1, 1 equals 0, 0 equals 2, 2 equals 1. Okay, they're basically just, you know, moving everything around. And I kind of liked this, but we're gonna do what they're doing first. So let's just go ahead and put it in here. So this is saying put the cards 2 now contains whatever was in cards 1. Get that right. And then do 1 and 0. You love Common Lisp, a strictly dynamically typed language without type declarations and with simple data structures. Interesting. Yeah. Build simulations for living. Nice. Very cool. Very, very cool. Welcome, by the way. Thank you for joining. So 0 and then goes to 2. So let's do 0 and we'll go to 2. So that this is moving around the values of everything. It's like swapping values around like a shell game. And it's kind of useless for trying to understand how the language works. I think it kind of obfuscates what we're trying to learn here, but it's fun. So we'll put that in. And I don't know if Lisp is using AutoCAD. I think it is. So here we go. We've got so I need to buy a C++. No, you don't need to buy C++. No. The first step to getting something where you can code on is to get yourself an interpreter. I would suggest Linux. That's been my preference for this kind of programming. But this book that we're reading right now, Bible study, this book that we're reading, Head for C, does go into that, and there is a Head for C++ as well, and it talks at the beginning of it about how to get something to you. You have to have a compiler to do it, and there's lots of ways to go about that depending on whether you want to do it for Windows or you want to do it for, you want to do it like for Linux, code for Linux and all that. And I'm a Linux guy, as anybody will tell you. So now we have Monty, and it shows us the QKJ. So it all worked and it didn't blow up. All right, so we were able to go through and see that this is broken, but the solution is not. And the rest of this discussion is about that. So when we have a pointer, the pointer is on the stack, but the pointer points to unchangeable content in the constant section of whatever this is, the memory, the read-only memory. And so yeah, we have read-only memory for the actual code and the constants, and so that was unable to mess with it. You don't need to buy a computer. If you have a computer, you can just put in a compiler onto your computer. Yep. If you're going to change a string, make a copy. So the truth is, if you want to change the content of a string, you'll need to work with a copy. If you create the string in the array memory, that's not read-only. There won't be a problem if you try to change the letters it contains. But how to make a copy? Let's just do this. So this is how you make a copy, by saying, hey, I want an array. And by doing that, that says I want to allocate the memory and a copy for that, and it makes it it puts the copy into memory, which is what we were just talking about. And remember that this is a warning about decay, like we talked about, pointer decay. So the computer loads the string literal. The string literal is down here, number one. And then secondly, it makes a copy of it. And third, it makes a reference to the copy of the constant. And it's sort of a waste. I think it's, I don't know if it's more of a waste, honestly. I kind of want to know that. But that's what's going on. It's making a copy. When we've done this, we've tested this, and this works all well. So let's move on to the next thing. In case of the magic bullet. So we're on to a new thing. This chapter 2 is the one that they told us to go through very, very, very slowly, because understanding pointers and memory is the single greatest challenge to see by far. So, you know, we're taking our good sweet time here to get through this. I'm going to actually save this to Git and GitHub. I'm going to save, let's do this. Let's say, wait. Add -a dot. I should probably add a git ignore on the other one, but whatever. Commit, say add Monty project with comments. And I'm going to git commit that. Turn my keys back on so you can see what I'm typing. All right. The case of the magic bullet. So let's just continue. We have about 15-20 minutes left, so let's do this. The case of magic, he was scanning his black catalog of guns and ammo into Delicious Library when there was a knock at the door, and she walked in, 5'6" blonde, with a good laptop bag, cheap shoes. He could tell she was a code jockey. You got to help me out. You got to clear this name. Oh no, that was the girl. I got the voice wrong. You got to help me out. You got to clear his name. Jimmy was innocent, I tell you, innocent. He passed her a tissue to wipe the tears from her baby blue eyes and led her to a seat. It was the old story. She'd met a guy who knew a guy. Jimmy Blomstein worked tables at the local Starbuzz and spent his weekends cycling and working with his taxidermy collection. He hoped one day to save up enough for an elephant. But he'd fallen in with the wrong crowd. The masked raider had met Jimmy in the morning for coffee, and they'd both been alive. Insert code. Masked raider equals alive, so that's a character array that can be changed. I mean, right? Character Jimmy, char Jimmy, masked raider. Uh-oh. Now we have a pointer to a change. This is a pointer to this, whatever, to the changeable stuff on the stack, right? And then printf, masked raider is %s is a string, masked raider, Jimmy, masked raider is alive, Jimmy is alive. Okay, so that prints. Why does it print? It prints because masked raider is a copy of the pointer that is pointing to the stack memory that is a copy of the stuff contained in the constants read-only memory space for string. I think I got that right. Then that afternoon, the Masquerader had gotten off to pull a heist, like 100 heists like he'd done before. But this time, he hadn't reckoned on the crowd of G-men enjoying their weekend on a 3-card Monty session in the back of the room at the Head First Lounge. You get the picture. A rattle of gunfire, a scream, and months later, the villain was lying on the sidewalk, creating a public health hazard. Dead. 0, 1, 2. I know what they're doing here. They're going to leave a dangling pointer with no null. I can see it already. I think that's what they're doing. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. So what did they do? They changed out the contents on the stack of this read-write memory on the stack that's being pointed to by Masquerader. All right. Problem is, when Toots here goes to check in with her boyfriend at the coffee shop, she's told he's served his last orange mocha frappuccino. Do people drink that? Printf, Masquerader is %s. Jimmy is %s. Masquerader, Jimmy. Obviously, this is going to work. Masquerader is dead and Jimmy is dead. Why? Why are they both dead? I actually know this one. I know this one without looking any further. Why is Masquerader pointing to dead and Jimmy both pointing to dead? Why? Let's code it. Let's code it. We'll call it Jimmy. How about that? Call it Jimmy. CD into chapter 2. Let's write this code and mess around with it and see why it's breaking, shall we? Make directory Jimmy. CD into Jimmy. They both point to the same memory space. Yep, they do. Yep, they do. I mean, that's the short answer. The short answer is this statement right here. What does that do? So, by the way, what is in a pointer? What is the actual value? It's usually a long integer pointing to an address in memory, right? So if you were to print out Masquerader or look inside of it, it would contain a number. And the number is the address in memory of the first character, 0, in this case A, in the stack. That is the copy on the stack, not the read-only constant section, which also has an alive in it because you used a string literal. And then when you do this, you're basically saying, so let's say the number, it was the number 25. Let's say 125. So there's 125. It's not. It's usually thousands or something. The address of alive, the address of the A on the stack is 125. So Masquerader has, the memory address 125 in it. And when you do this, it says, give me a pointer to that. Give me a pointer to that pointer. Pretty sure they're the same number, but we're going to find out. Whether they're the same number or not, that's the reason that prints out that way, because they're both pointers and they're both pointing to the A on the stack, which is the string literal, and then, not the string literal, the copy of the string literal. In the string literal in read-only memory, it's not, because it's not read-only memory. That's what the whole last section was about. I may have misstated it. So it's the copy. So Masquerader, the content of Masquerader. By the way, let's code this, because what if I had made this a pointer instead of the array? Then it would be pointing to the constant in read-only memory. It would fail, right? We just did that with the last exercise. Let's do that over. This is super important. So and I'm just saying that's why I'm justifying doing it so much. So let's say Jimmy, and boy, talk about understanding how your computer works. I mean, this is why people should learn C, is it does make you really, really understand how your computer works. All right, so include stud.io so we can use all that stuff. Int main, and we'll throw a return in here so I don't forget. Return 0 is success. All right, so first steps first, we'll say, yeah, if you can't code C and understand memory management, don't use the word engineer. That's it. I like that. That's a good point. At least for me. For me, if you don't know everything that I'm talking about and understanding how memory moves around and stuff, that's why I don't call myself an engineer. I call myself an engineer with regard to infrastructure. But when it comes to software engineering, yeah, if you can't describe how your software is affecting the underlying system, how can you call yourself an engineer? In my mind, people disagree. But I think you're people who write Python code, machine learning, data science people do web stuff. That's fine. You guys are talented, smart people, but you're just not engineers. You're not. You're developers. You're putting things together, and people strongly disagree with that statement. And that's just my thought on that. I'm not the only one. That's not an original thought. A lot of other people believe that way. So can't write it safely. Yeah. So it makes a good question, right? If you declare Masquerader as a constant charge, blah blah blah, it will print the read-only memory address. Interesting. Spicy Bible, Spicy, you have to say what it is you want to do, in my opinion. before you can start looking into titles and stuff, I think the question is, what do you want to do? And we talk about this a lot for our beginners. What do you want to do every day? What do you want to make? What are the results? What are the high level gains of what it is you're doing? Are you in it for the money? Are you in it because you want to build a project for yourself or your children? Are you in it because, what are you making? And then your title should be defined by that. And then you should also pick the technologies that go with whatever that occupation is that you're going for. If you're just trying to get a job, then there's lots of stuff there. Runs off to dinner. Yeah, it is time. We're almost done here. Ryan, take care if you have to go. I am about to wrap up. So let's go back to this. Wait, we have it in the book here. So, okay, so Masquerader is a big old long one. So we're going to do char Masquerader equals alive, which is exactly 5 characters. I'm going to ask right now. Anybody want to guess what would happen if you tried to put more stuff than those 5 characters to replace with dead? What would happen? You probably can guess. We can blow it up and show you. Masquerader is blank. Jimmy is blank. Masquerader Jimmy. Masquerader is Jimmy is overflow. Yep. Short answer is yes. You know what? Fuck Masquerader. I'm just going to put Raider. I hate long identifiers for no reason. You know what? Python people do that all the time. It drives me nuts. It's okay to have short identifiers. Make the length of your identifier names coincide with the scope. The more localized the scope, the smaller, down to a single letter. But if it's in a function, maybe make it a little bit more, disambiguating or whatever. And if it's really big, like it's like a constant for the whole thing, go ahead and use a big old long fucking whatever. I hate it when people unnecessarily make long variable names. It's a big pet peeve of mine. The answer in C is to go. So Raider, and then we have Jimmy. So Jimmy, a char pointer Jimmy equals Raider. Thank you for that. And let's try this. I see, Spicy Bible Study. Sounds like you're just a troll. Welcome, good trolls of the world. You're obviously a troll. But you're welcome anyway, as long as you don't get off the chart. So, there we go. Masquerader is alive, and Jimmy is alive. Both of them are alive. Yeah, right. Okay. Go for it. Spoken like a good troll. Doesn't break character. We know this. We know the skills of trolling. We are acquainted. So, let's go. Biology degree. Yes. Yeah. Sorry, Spicy. You know what? I'll time you out. That it's irrelevant. I mean, read the room, dude. This is not the time for your random shit. It even says so in my about. I know you're new, but give a timeout. If you survive that timeout, then and you come back and you actually have something interesting to say that you're serious about, we'd love to have you. All right, so this is why people on YouTube say you should shut up your Twitch chat. They're distracting you too much. I read a comment today that said that. That's exactly why. They're like, stop looking at the chat. Just code and teach us how to code. We don't want to see what everybody else has to say because of people like Spicy who don't read the room. All right, so here we go. We'll go back to here. So we're actually going to change the values. We're going to change each individual value. There's another way to do this, but let's do it this way before we wrap up. We're getting very close to the end, but I did start late. So, all right, so let's do this. First of all, we're going to put another one of these, right? And then we're going to do this. We're going to say, Raider 0. Oh, no, is it Raider or is it Raider? Yeah, okay. Raider 0 equals D. You know what? I can write some bash code here. Watch this. Watch this goodness. For I in DEAD exclamation point. Do echo. Actually, printf. 1, 2, 3, 4, 5, 6, 7. Was it char? No, Raider. God, I have to do. Yeah, oh well. I didn't. There's a better way to do this. I could have made it in right. Writing code, write code. Equals. The letters are the hard part, though. So we'll do that. I. And done. Bash. There we go. Pretty cool, huh? Writing code to write code. Bang, bang, bash. There. Now I... 0... Hey. Yo, dog, I heard you like to write code. Yes. 3, 4... So there we go. What are we going to have now? We were all wrong on the latest spec. Yes, we were. Yeah, we covered that, Taniwa. Did you like that? Did you like that writing code with code? Do I need to tell you further to learn Bash? I'm just using a Mac keyboard. It's the best keyboard used. It's the keyboard preferred by the most Nobel Prize Peace winners, the most novelists, the most journalists, and the most people who matter. If you want to fight about your blues and your reds with your mechanical keyboard and ruin and create sound pollution for the rest of the office and the world forever, and ruin your wrists in the process, be my guest. I am not going to apologize for my Mac keyboard. It's fucking awesome. And it's medically, objectively the best thing to use. So, here we go. Learn Bash, but also learn Vim. I agree, yes. All right, so now what are we going to get? We already kind of predicted this. So... Jimmy, that's fine. Jimmy is dead, Jim. We should have turned this into a Star Wars thing, a Star Trek thing. Come on, Jim is dead. Jim is dead and Kirk is dead. We need to change this. Yeah. Okay, so far so good. We're doing exactly what it says here. Now, once again, okay, so a little quick pop quiz here for myself and others. What happens if I do this instead? Pop quiz. Pop quiz. Pop quiz. What will happen with that? Pop quiz. Thank you. In fact, we'll get rid of these. Shh, don't tell, but that would blow up if we did it. It's okay, fine, reverse. So make, hey, look, it compiled. Look. That is okay. I'm pausing for effect. I'm pausing for effect. What does it make a pointer to the place of memory? So this is a pointer. Yeah. So we're going to fight about keyboards in my stream while I'm doing a live stream to YouTube. Let's not, please. Thank you. So, so Raider equals alive and Jimmy equals Raider. That means that these things have exactly the same pointer in them. This is fine. What I'm trying to tell you is this code is totally fine. Yes. Yes, yes, yes. Yes, Duffy, that's right. So the only difference between this and this is that when I had the pointer in there, well, I'm going to show you. So this code is all fine. This is completely fine. When does it get not fine? Why? Because the pointer, God damn it. The pointer, that was cool, kind of. But this is going to blow up, right? Hey, proportionate. But this is going to blow up. Because now this pointer, which is pointing to read-only constant memory, is read-only. Yes, it is. And we're going to make this, and it's going to blow up. Kaplooey. So that's why. Because these writes, it's trying, it'll happily give you a pointer, but then when you go try to write to it, now we already saw that the way to fix this is to put a const here. But we did that in the last exercise. There's actually two consts there, and then it blows up at compile time and not runtime. But this, I'm going to put wrong. I'm going to keep putting it in here because I really want to emphasize that point. Okay. Now this will work. Why? Because this allocates a copy on the stack of the constant string literal, which is written in the read-only constant section of this of memory, right next to where the code is, in the read-only section where the code is. Or is this stuff talking? How do you know when you're leaking memory? I don't know. I think there's like profilers and stuff like that, but mostly I think you need to learn to do safe coding practices, such as, if you're going to use a pointer like this and you know you're not going to change it, you should probably put const in front of it. And we already talked about this. This will save you at compile time from things that would blow up otherwise at runtime. So is there a thing called Valgrind? I'm not familiar. I'm sure there's awesome tools to look at that. I don't know what they are. So if anybody out there has good answers to the question, how do I keep from memory buffer overflows? I want to profile my code. Please give us that information, because that's a big thing when you're writing C code. Some memory leaks. Yeah, so far no memory leaks yet. I mean, we're close. We're reading off the ends of stacks and stuff, but all right. So this is wrong. This is right, and our thing is working the way we intended. Now they're gonna say, well, I don't want Jimmy to die, right? Why is Jimmy dying as well when the raider dies? Because they're pointing to the same thing. Now let's actually, I want to prove it. Let's see what the actual values of the memory addresses are. And to do that, we're going to do that at the very end. Okay. So let's do another printf here that's not required, but I want to do it. So let's say, and I believe it's an li and another li. And we could say raider pointer and then put a backslash in there, and we could put Jimmy pointer, and this will give you the actual value of the pointers. You can see that they are either the same or different. Raider and Jimmy. That should work. Nope. I got that wrong. Long int. What did I do wrong? I think I have to cast it as a pointer. I do. I think I do. Expects argument of type long int. Wait, what? That's interesting. Oh, P. Right. Thank you. I'm so indebted to you. Yes, y'all are brilliant. Thank you so much. So as you can see, the pointers are the same address. And that's why. That's what's up. So this here, so after this finished, the Raider pointer, that's what this is, contained an integer, and this assignment put that integer, that address, pointer, whatever, into Jimmy. And this is, again, so that's the same thing. So now they're the same. And that's why they point to the same thing. I'm interested to see what the rest of the book says, and we can wrap up here. We're almost done. So what gives? How come a single magic bullet kill Jimmy and the Masquerader? Because the pointers are pointing to the same thing. In the case of the magic bullet, how come a single magic bullet kill Jimmy and a Masquerader? We just did this. Jimmy's blah, blah, blah. We already covered all this. I just talked about all this. I don't need to do it anymore. So here we go. It took a detective a while to note the mystery of your head first brain booster fruit beverage. He sat back in his seat and looked across the desk. I'm afraid I got some bad news. Jimmy and Masquerader we're the same person. Okay, I get it. You'll remember that. Masquerader and Jimmy are both pointing to the beginning, specifically the first character at the beginning of the string. I'm in a lesson, so I can't really talk right now. I'm just about done. Wrap up in the next 10 minutes. So then what we have? Jimmy and Masquerader just alias for the same memory address. They're pointing to the same place. We just proved it. When Masquerader stopped the bullet, so did Jimmy. Add to that the invoice from the blah, 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 blah. All right. Shut case. Bullet points. If you see star in a variable declaration, it means this variable will be a pointer. Ironically enough, this is also a pointer. Masquerader is a pointer, but this says, hey, I want a pointer that's pointing, and this says, hey, but I want to allocate a copy of this string literal and then create a pointer to that. And I don't particularly like doing that. In fact, to me, the only practical purpose for ever doing this is if you want to change the value. That is the only reason to do this. I personally think it's bad practice in C coding to do that at all. I think you should, I would rather use malloc or any number of other things. If you want to change the exact one that's being referred to. Shh, we're on a roll. Wrapping in 10 minutes. Did I really? I don't think I said that. Did I? I'm afraid I got some bad news from Jimmy and the Masquerader. She took a sharp intake of breath and raised her hand. Bloom. Okay, we're done. Where's the bullet points? String literals are stored in read-only memory. Oh, this is the end of the chapter. Holy shit. I use swear words, in case you're wondering. This is both for me to remember it. Yeah, Mr. Yan, last C code I wrote was 12 years ago, and I don't think I knew what the fuck I was doing. Of course, I didn't have to. I did do a lot of memory. It's easy to find out when something's blowing up, and that was my job. About the same time I was doing debugging of code that was breaking C code. Having to write fresh C code, most of my fresh C code didn't have to be as pristine as this, and I just did what I saw on the internet. So this is my first real deconstruction of what's happening with C under the hood. And it's also going through this really wonderful book for beginners, textbook with blue C on it. Yeah. And that book is kind of dated. We were reviewing that the other day, the KNRC book. Yeah. If you want to modify a string, you need to make a copy in a new array. That means if you want to modify that string. The danger of doing that, by the way, is if you make a string and then you try to modify the content of the string and you go beyond the original size of that string, all kinds of hell breaks loose. Because you haven't allocated enough space for that string, which is why I think this notation is just dangerous. I don't ever want to use this. Somebody who knows more than me, tell me that that's not true. Tell me that this is just bad practice, period. That you should never do this. Because the purpose of, okay, let me prove it. I'm going to do something the book's not doing on purpose, and we'll end with this. All right. So let's say you just read the book casually, and you come away with this sort of naive notion that if you use a pointer, you can't change it. Therefore, I'm going to use an array, and I can change it however the fuck I want to. right? And it does make a copy at initialization, but this is what I want to know. I'm pretty sure you're limited to an array of that specific size, a string of that size, because that's part of the initialization. So there's kind of an implicit malloc going on for the number of characters that are used, including the null at the end. But what happens if you try to do this little funky thing and you want to be, I don't know, let's say you want to be really verbose, right? Let's say you want to be really verbose. You're like, well, I can change it because I made it an array. I made an array with a string literal. That means I can change it if I want to. So there. And somehow you come away thinking that you can change what doesn't exist, and then you get all kinds of trouble. And I personally don't think they made a significant issue of that. There you go. That's no longer an alternative string. You just blew the fuck up. And not to mention the fact that you could do this. Here, let me try this another way. I don't know if this is possible. Oops. I don't know if this is possible, but I want to try it. I want to see if I can take the predefined rater and I can use string literal notation again. I don't think you can. I don't think you can do this. You should never use string copy because it's yeah. All right. So let's see if I can even do this. This is how you might write it in Go, right? You might write this way in Go or in Python or something. It's intuitive. It's probably incorrect, but let's try it. Let's see what happens with that. So, oh, look at that. That won't even build. Oh, because of semicolon. Okay. All right. So, rate equals dead. Sorry, no dice. Error assignment to expression with array type. So this is my personal take on this is, first of all, wanting to put S the character array that you're changing individual letters in, don't even think of it as a string in the first place. It accepts the size, yes. And Go are immutable, unlike C. This is true. Yes. Yep. So what I'm thinking here is that, I mean, that you should never use mutable strings, period. And you should do what Go does by default. That's what I'm thinking. So this is wrong, right? And it's like wrong, right? You should do this. Now, and I personally think the better way to do this, and I would probably do this, because honestly, if you're going to be changing individual values, that means that you are building more of a bit field or a character field. And, then you're doing, I mean, this is not a practical application. I think if you're doing this, the better way to represent this personally is to say, no, I actually have a fucking character array and I'm going to use a character array, and people may not like this, but the number of times you're actually going to want write access to the individual character elements of the character array is so off and odd and rare that in those few times that you're going to do those things, you should just use the character array. And then, by the way, you should never try to use that as a string ever. Right? These two are the same, but I personally like this one better. And the reason for that is because it's exactly the same thing, except for I know what I'm dealing with this one. With this one, I know what I'm dealing with. That means I can change all of these things. And that would make it easier for the next person. Yeah, absolutely. Because they see what's going on. If they see this and they have any Go or Python background, they're going to be like, oh, hey, I can swap it all out. And then, or else they might ask a question, why are they changing every individual letter when I can just set it like this, which you can't. It should just blow up. By the way, that blew up at compile time, thank God. I mean, if that was not a compile time error, that would be even worse. So, we're getting really pedantic on the C stuff for all sorts of reasons, which I like. But that totally works. Oh, no, it doesn't. What the fuck doesn't that work? Oh, because of this guy, right? Because why? It doesn't exist. There's not one there. Actually, what's crazy is actually if we were to print out each of the individuals things, Wait, I have a different question here. Uh, I have to do this. I mean, if I'm dealing with it as a character array, what if I do this? Is this gonna automatically allocate enough space? It's a different error. This is a different error, right? So the error we're getting right now is because printf is trying. Yeah, now we should have stack eruption. So this other one is, hey, I don't have a stack. I'm writing off the end of it because there's no null with a foot gun. Yeah. Yeah, I think you're probably right. So that compiled, still blew up. Why did it blow up? It blew up because memory access at offset 38 overflows this variable. All right, so let's get rid of that overflow and let's produce the other error. In this particular case, this works very happily. It replaces the null byte at the end, which says, hey, I am the end of the string with an exclamation point, which is a different error. Different error. Say it doesn't overflow. So let's try this. Let's try this one. I want to read this error. Because this error is now going to say something like, hey, you tried to printf a thing, a string with no terminator. Watch. It's going to say something about null termination or something. Yeah. Oh wow, it was smart enough to catch it. This may be a false positive if your program uses some custom stack, unwind mechanism, swap context, or vfork. Same problem. There it is right there. Ooh, look at the stack error even. Wow, isn't that cool? Oh god, that is so cool. So it's like I'm gonna write here. Wow. F1 stack left red zone. Wow, that is so cool. Stack right red zone. This is neat. I like it. You know. So both of those are bad. There's like a foot shot. Trying to read past the end of the array. Yeah. In both cases, it reads past the end of the array. Yeah, because the size of the array, it hasn't allocated memory there. So it's not magically going to add extra elements to the end of it. And this is one of the things that Go abstracts away from you. I'm going to advertise for Go a little bit. But in Go, it definitely does do that. It fixes stuff like this. That's why you have to use append when you want to make a string bigger. You have to use plus or concatenate, and that will take the two things, and underneath the hood, it'll put them together in the right way. And it's why Go has things called slices instead of arrays, because slices are abstractions on top of all the underlying memory, and slices allow you to look around. You can even reorder things because the underlying array that goes with the slice matches, and so you have this extra abstraction on top. It's really brilliant, actually. Slices are absolutely brilliant. I just cannot overstate it. It kind of makes me sad that people that have a high appreciation for like low-level computer science, programming internals don't recognize how awesome that is. One of the biggest things for him with Go, yeah. And so that's those kind of things save us. We haven't even got into that yet with arrays, but those things really matter once you've dealt with the low-level stuff. As if you are an underlying string. We haven't talked about slices. Slices are a specifically unique Go thing. If you know about Python, anytime you hear the word array, usually array or a Python list, you're talking about a slice in Go, almost always. And they do have arrays, but the arrays are immutable. They're totally immutable. And slices are mutable. And they are on top of the array. They're an abstraction on top of the array that allows you to do Python-esque like things or JavaScript-like things with the list kind of logical data type, if you want to call it that. And so it's actually really cool. Really like it. I think Jimmy's dead, and we're good to go. And with that, we are going to close up chapter 2. It looks like that's not the end of chapter. Oh, look at this. Oh my God, we're going to actually dig into the steep hack. And oh my God, I can't wait. How much time we got? Can I go through this right now? 2.5, string theory. Okay, let's finish up this section. We're almost done. This is great. Okay, I'm so excited. You can declare sharp the pointer as const sharp pointer to prevent the code from using it to modify the string. Hey, look at that. They didn't do that anywhere. They didn't do that anywhere, but that's the way. The takeaway is use const. Whenever you use a sharp pointer, put const in front of it. All right, so there are no dumb questions. You've been expecting by your wife. No, I didn't. I don't. No, that was my stepson, and I heard him say 10 minutes, 15 minutes ago. Yeah. I mean, I could go check on him. I want to read this anyway. We're almost done. He was just going to comment on something about the videos that were on. And yeah. Anyway, it's fine. Don't worry. You get it. Every language that supports it. Use const anywhere. Yeah, you should do it anyway, right? Home minister. No. Why didn't the compiler just tell me that I couldn't change the string? Because we declared the cards as a simple character pointer. The compiler didn't know the variable was always going to be a string. Why are string literals stored in read-only memory? Because they're designed to be constant. If you write a function to print hello world, you don't want to write some other part of the program to write hello world string literal. Do all operating systems enforce read-only rule? The vast majority do. Some versions of GCC on Cygwin actually allow you to modify a string literal without complaining, but it is always wrong to do that. That is what we freaked out on yesterday. We got it wrong, though, but that's what we were all freaking out on. What does const actually mean? Does it make it a string read-only? String literals are read-only anyway. Const modifier just means the compiler can play up early if you want to. And that's what we've been saying. That's why you should do it. I love this book. This book is like really, really winning me over. And if you know me, that's a big thing to say. I don't hand out praise easily. Do the different memory segments always appear in the same order in memory? They will always appear in the same order for a given operating system, but different operating systems can vary the order slightly. For example, Windows doesn't place the code in the lowest memory addresses. Interesting. I still don't understand why an array variable isn't stored in memory. If it exists, surely it lives somewhere. When a program is compiled, all the references to array variables are replaced with the addresses of the array. So the truth is that the array variable won't exist in the final executable. And that's why the assembly code looked the same. That's okay because the array variable will never be needed to point anywhere else. That's why looking at the assembly was always pointing to stuff in the constant. In the stuff in the heap. That's super. That means optimizations are like that's why we didn't see anything in the constant section. Because the optimizers were not doing it. That is super cool. I'm glad I understand that. If I set a new array to a string literal, will the program really copy the contents each time? If I set a new array to a string literal, which we just did, will the program really copy the contents each time? It's standard the compiler, the final machine code will either copy the bytes of the string literal to the array, or else the program will simply set the value of each character every time it reads the declaration. And that's the optimizations that we saw when we put it into Godbolt for looking at the machine learning stuff. Assembly. You keep saying declaration. What does that mean? A declaration is a piece of code that declares something is going to be a variable, a function, and it declares this exists. That's not the assignment. Assignment's with the equal sign. Declaration is everything to the left of that says, hey, this is the thing. You can do declaration and assignment in one shot, or you can do declaration by itself. So there. Why is scanf called scanf? Scanf means scan formatted because it used to scan formatted input. Yeah, it's a scanner. And that's, if you don't know about compiler theory and stuff and scanners and parsers, then that's where the scan comes from. Memory memorizer. This is going to be really fun. I think this is the end here. So I really, this is the final, what page is this? This page 80, I want a screenshot of this shit. I want a screenshot of this. Because this is the most confusing thing I've ever gone through with C. People who know more than me are constantly referring to the stack, the heap, and memory, and read-only memory, and all that stuff. And I have no mental model for what the fuck they're talking about. And this has really helped me with that. I really appreciate this. So I'm going to take a picture of this. You can too if you want. But because this is like one thing I want to pull up a lot. When I'm talking to people about it, I want to show them. I want to kind of put stuff in their head. I know it's sort of plagiarism. I can make my own picture later, but God damn it. All right, how about that? Oh wait, I'm making a screenshot. Let me. You guys know about my that thing, right? That screenshot. I have a tool for screenshotting that I built. It combines a bunch of other existing tools. And I want the page number in here because I want to be able to go to it later. So boom, screenshot, and push enter. And there we go. So what do we call it? We call it the memory organization. An ASCII version, please. What need you see working by? I don't know. Good question. 22222. Yes. Here you go. By the way. Oops, sorry. So if you want that little screenshot, I'll send you a copy. Here you go. So here's my. It put it in my GitHub for me. And yes, it's technically that's plagiarism, but that's definitely within fair use because I just took a single thing. So, so there you go. If you want that little screenshot. All right, so let's actually read this. So let's zoom in again. And read it, and then that'll be done for tonight. We're way over, but I don't care. Stack. Does this say Atari ET? Heap, stack, heap, globals, constants. The globals are changeable, constants are not. And then the actual code, the assembly code. Okay, so stack. Stack is the section of memory used for local variable storage. Every time you call a function, all the function's local variables get created on the stack. It's called the stack because it's like the stack of plates. Variables get added to the stack when you enter a function and get taken off the stack when you leave. Stack, by the way, is something you learn about in data structures and algorithms if you go through it. How to create a stack structure or algorithm, the idea of putting something on and popping stuff off. You're going to hear the term stack a lot in coding. And yeah, weird thing is that a stack actually works upside down. It starts at the top of memory and goes downward. That makes sense though, because it's easier to add something to the end than add it to the beginning. First on, last off. Yeah. And that's because it's always easier to append to the end of something. You'll find this if you end up writing like any kind of systems for anything, that when you run into it, it's always easier. Imagine trying to deal with a log if you had to write something to the top of the log every time instead of to the end of the log. You'd have to rewrite the whole log every time because all the memory would have to shift down by one. That's not necessary because there's always some extra free memory at the end that you can add when you're dealing with something like the stack. So you're going to see stuff is always going to be reading and popping off the end. It says pop, but it's really pulling it off the end, I think. So yeah, heap. Heap is a section of memory we haven't really used yet. The heap is for dynamic memory allocation. Somebody said malloc. Heap equals malloc. And we haven't talked about malloc yet, which is cool. It uses it a lot. You'll see later in the book how to use a heap. Globals. A global variable is a variable that lives outside of a function. It means there's no curly brackets around it, usually. Globals get created when the program first runs. Most globals, by the way, if you're talking about constants, well, let's talk about constants first. Constants are also created when the program first runs, but they are stored in read-only memory. Constants are things like string literals that you need when the program is running and you never need to change them. They didn't talk about this at all yet, but it's actually I think it's actually rare and even sort of an anti-pattern to use global constants, because global constants can be replaced with macros, and macros will replace the actual value into the code, and then they will become constants. So they ultimately end up becoming constants anyway. But yeah, make a structure. Stack is like brick, and heap, and heap is like ton of stone for making a structure. Nice. I like to think of it. Oh, that's a nice way to think of it. I like that. I like that a lot, actually. Yeah. Yeah. Globals, constants. There we go. There's constants there. Constants are read only. We talked about that. String literals are used there, but you can also declare them yourself. Code. Finally, the code segment. A lot of operating systems place the code right down in the lowest memory address. The code segment is also read only. This is the part of the memory where the actual assembly code gets loaded. And if I understand it correctly, it is assembly code. It's like, it's not, when you live at higher level languages like interpreters and bytecode and all that stuff, you kind of get used to thinking of, oh, there's always something underneath this, right? Like if I write this C text code, it's going to be compiled into an ELF binary, et cetera, et cetera. In fact, I would really like to, the next thing I want to do after this is rip apart ELF binaries, because the ELF binary is the thing that comes out of this. That's computer architecture. It really is assembly. Yeah. So when we do let's actually look at the file. This is something you can't do in other editors very well. This is the binary. We're looking at the code in the binary, and this here is machine code from what we're hearing, because this is the highest level of the stack. This is the lowest. The lowest level of the stack means it's the first thing in. So that's this stuff here, I'm assuming. And as you get down here, we start to see the strings and stuff. So I'm guessing that this is a constant space down here. I'm sure there's like an ELF binary visualizer someplace. And if anybody knows about one, I would love to find it. Gas, NASM, or LVR. I don't know what that is. LVM, yeah. So again, here's more data. I'm trying to just, it's first thing. Look, there's our pointers. So that's how we know we've hit the constant space, because now there's a constant. That's a string literal, right? So we're starting to see string literals. By the way, if you want to, we did this on the hacking day, but if you want to see all of the string literals, just type strings Jimmy, and it will show you every string literal stored in the program. This is every string literal that was stored inside of the final resulting binary. And there's a bunch that are included for us. And then there's our own ones here. There it is. See? So here we have Raider pointer. We have the Jimmy pointer. These are our literals. This is why you should never hard code a password as a string literal. People do it all the time. How stupid is that? Raise your hand if you've ever found code in production that had passwords hard-coded as string literals in C. Because I have. And I can't tell you how fucking stupid that is. It's like so stupid on so many levels. It's just so stupid. It's compiled. No one's going to get to it. No. They think that somebody can't even look in it, whatever. If you're a hacker, that's one way to really own dumb C programmers. And I think we're done. So this is some homework written in Rust, I believe. ElfCat. Oh, nice. If it's, who gives a shit if it's written in Rust? If it lets me look at ELF binaries. Yeah. I kind of want to do that right now. Can I do it without Rust up? Damn it. You're watching me install Rust. Install cargo. Yes, fine. I'm sure there's like a version that doesn't have to use this, but whatever, we're gonna do it. I'm gonna catch shit for this. I know it. And oh, my fan just went completely crazy. I don't know what the difference is. The internet wins. So cargo install elfcat. Oh. This very quick. Somebody snipped me installing a Rust app. Knows how long it takes. It's the only time I've ever heard Gamozo complain about Rust. It's compilation. I know, I just installed it off of cargo. I didn't even look at my cargo because I trust the cargo people. Bad me. Bad me. I just probably, violated myself in some horrible way. I kind of don't care. Elf edit. See, look, Elf edit is the kind of thing I want to see more Rust people making. Anyone can add to cargo? Are you fucking kidding me? Are you telling me cargo is the AUR? I feel even dirtier. Don't be me. Don't do what I did. But at least there's some traceability, right? There's not in the AUR. You just put whatever you want out there. Comes from crates.io. I think it does, which you can't read, by the way, with links because it does. You have to have JavaScript to read crates.io. The card was reposed. Okay. Nice. Elf edit. Well, I guess we have to give it a thing. The options are what? Update the elf header for elf files. The options are... No, I don't want to do that. I just want to read it. Oh, damn. Oh, damn. I wanted someone to visualize my elf binary. Rust Subs community. Aha. Output type. Input OBS SC. Can it not detect that? I mean, it should be. I guess it can't detect it. I'm trying this. Input dash OSABI Linux. Do I have to do a capital Linux? How stupid is that? Still no goodness. Options, elf files. No joy. I'm very sad. I'm very sad. I'm pointing to an elf binary right there, and it's like, doesn't know what the fuck to do. How about this? Elf, I should know better. Elf edit, which, watch me break my LS on my system. Nope, can't do it. Update the elf header of elf files. It's okay. But you got to show the part. It's actually, I'm using elf edit, not elf cat. Is there an elf cat? Am I using the wrong thing? Path to file. I'm doing what you said and it's not working. You know what? This is a fail. You're making Rust look bad. You're making Rust look bad. I'm doing exactly what it says. Am I not? I installed it at great expense in time and energy. And then what? I did elfcat path to file and got nothing. I get nothing, people. I call bug. I don't want to call this a bug. It's too bad because they could have had a real chance to impress me and they failed. If anybody runs anything in my .repo or anything in my repos at all, they have the same experience. So I can't judge, but still, I'm kind of pissed. It's called elf edit. Oh, it's elf cat. Did I install the wrong thing? Pretend I didn't say anything. God damn it. God damn it. But I installed elfcat. There's an elf edit? Where the fuck? All right. I stand corrected. I am very glad I was wrong. There. Is that what you wanted to hear? Somebody throw a jab in there. That's because you're a Go programmer and you make those kind of mistakes. That would be effectively, yeah, are being emptied as we speak. None of my crypto wallets. There's no elf cat. What the fuck? Oh, God. You just forced override. Did I type ETF? Please tell me I didn't. What am I doing wrong? Is it out of my cargo bin? Did I take cargo bin out of my path? I did. I did. I did. What? All right. Well, at least we got that now. Yeah. Oh, those Go programmers. What the fuck? Why is this? Path and Pen is really cool, by the way. You want to do this. I promise. You really want to do this. It's pretty damn awesome. And then you don't have to fuck around with path every time. And you can build your path dynamically. That's in my .dot files. If you want that, it's in my bash RC. Yup. Oh shit, what did I break? I broke my path is what I broke. I broke my path. It's not happy now. Which yeah, I can't find it. Anyway. Elfcat is not working. I mean, what a great name. That was the first thing. So Elfcat, and I definitely stole it from somebody else, so I don't get credit. Elfcat Jimmy. Why is there a fucking Jimmy.html? I didn't make that shit. What the hell? What the hell? This must be examined. Look, if it gets us closer to understanding the stack and the heap. Whoa. I take back everything bad I've ever said about Rust. Not everything. Anything about the community or the syntax, I maintain. This is pretty fucking nuts. This is like a binary. It's XXD, it's all it is. It's XXD with sugar. It's XXD and a sugar. With sugar. Yeah. It tells you what kind of thing it is. So it actually did cat it. It just wrote it to a file and did nothing and didn't tell me it did it. Typical Rust program. Just something fucking amazing and then don't tell me how to use it. So I have no idea what these arrows are, but they kind of are cool. I mean, I'm trying to make sense of it. So where is the, wait, is this the heap? Yeah, it is. No. Is this the global section or the constant section? I think this is the constant section. Yeah, that's the constant section. Yep, that's the constant section. Oh God, this is going to make me such a better hacker. You just clicked memory for me. What? Hey Rob, how's it going? Just clicked. Look at this section. What? It's just so big. It can't. Wait, what? Wait. Oh my God, my eyes. My eyes. Oh my God. Oh my God. Oh my God. This is so cool. Those are pointers, yes. They are. Holy shit. Yeah. Because it shows you like the collective translation of it. It's so fucking awesome. Elfcat, you won me. Okay, there. You remember I kept saying there's nothing good written in Rust and I make fun of it? I'm gonna have to stop saying that now. This is fucking amazing. This is so amazing. And you can see the pointers. Yeah. So you can see the stuff in the heap allocated to the pointers if you really want to follow it down that way. That is crazy. That is crazy. So this is going to be, what is this? Section headers. Sim tab, string tab. What are these? It's a different section of the constant section, I think. Index 35, index 36. It gives you the name over here too. This is the shared string tab is the name. And this stuff over here is gonna be relative to the identifiers in assembly when we get into assembly. Oh my god, this is so cool. Prog bits. Oh, look, this is prog bits. So this is the program. This is the assembly of the program. Offset in file. Oh my god, it gives us. Holy shit. It gives you exactly what it's doing. It has the assembly in it too, with like some definition of what the assembly stuff is doing. Shared name, shared pointer address. And so you can like, oh my god, you can like hover over the assembly section. I mean, that's just amazing. Talk about forensics and zero-day discovery. Anyways, that it output from something like XSD was the memory layout, and after seeing this visual, yeah, well, we knew it was the memory layout. I mean, I knew it was the memory layout of the binaries all the time. What I did not know is the organization of the memory, which is what this is. It's a nice, pretty picture of the same thing. We have a stack up here. We have the heap, and by the way, the stack isn't in this, right? Because the stack gets this. How much stack is assigned to each running application? Because I thought the heap isn't because you're using allocated. Oh, right. We're not using. Yeah, the heap's empty in this because there's no malloc. In fact, where is that? It should be totally empty. Yeah. Where's the heap? Let's go find the heap. Oh, file header. Yeah, of course. God damn, this is cool. By the way, have you ever noticed that the elf elf identifier at the very beginning is exactly the same number of bytes as a shebang? So the operating system reads those first bytes of the file, and that's how, or the bytes or bits or whatever, and that's how it tells what it thinks, whether it's an interpreted thing or it's an elf binary. And if it sees the elf binary, it's like, oh, you need to go over here in memory, like directly, and blah, blah, blah. If it's a shebang line, it's like, I need to keep looking. Where do I need? And it looks at the path, goes to find your interpreter, and then it sends the interpreter into memory and then passes the whole file to standard input to the thing. It's super cool. I mean, if you want to know actually how your computers are running and working, and how those files turn into running memory, it's super cool. The grow the heap is set BRK, is it? And is it? It's not. Yeah, elf file header, offset the version. I should read a man page on that. I will at some point. Segment programmer headings, version address in memory. So where's the heap? Segment program header. We're still in the header, so this does not look like the stack to me. Heap is, yes. Memory depth from application. Yeah, that's what I was gonna say. So the heap memory, just the binary. Yeah, heap and stack are created at runtime. Yeah. Heap used by exec. Yes, it is. Yep. So that is super cool. That's like really, really cool to me. this is all this stuff. So what we're trying to say is, and they don't really talk about it here, this big section stack and this section heap is not created, is not in the binary. These two things get created at runtime. So when the program runs, then it does whatever it needs, and it inflates the stack and the heap based on the calls to get memory and all the memory additions and everything. So this stuff all gets created later. But this stuff is in the binary. Actually, no, that means globals are allocated at runtime as well. It's only the read-only stuff. Interesting. I mean, I think it's safe to say that the read-only stuff, yeah, because globals are just like any other variable. They just have to be global in scope. So these are at runtime allocated as well. So globals, heap, and stack are allocated at runtime. The read-only stuff is in the binary when it's compiled. If I got it right, if I have that right, that's really interesting. It depends on the global. Yeah. Heap and stack may be built into the OS core. Interesting. Could be heap. Yeah. That's super cool. All right. Well, I like that because that's like really good. That's going lower, and that's the reason I'm doing this. I'm doing it going through the book because I'm just looking for C for everybody else, but for myself, I'm super interested with the low-level internals of how C processes things, particularly on Linux, and what that looks like in the final form. How the data at the lower. I keep digging deeper and deeper into what is actually happening. Where are the electrons going? And because this is, if you were getting into computer forensics or security forensics, stuff like that, you need to know this. And I have looked at a lot of core dumps. That was part of my job, but I mostly just had to find out where stuff looked weird. And I didn't, if I had had a low level knowledge of this kind of thing, I would have just eaten that job up completely. But the number of people who can even look at an ELF binary and even begin to attempt to understand it is pretty low in the world. So most people don't want to do this. I guarantee you none of my peers do. None of my current peers they may be interested in it, but not to the level of wanting to look at this stuff. You can get, a kick-ass job and never ever give a damn about what's happening in low-level internals. I actually really care. I think it's cool. Yeah. There are even pointers. Yes, I'm super glad that repo worked. I was just a dummy and used the wrong thing. What's that? It's really burning my eyes. I'm sorry, people. I have to turn away. I must turn away. I cannot. My dark reader will not work on local stuff for some reason. I do not know why. So yeah, this is definitely not something I could use in links because it's got highlighting. This is, by the way, this is a legit use, in my opinion, of JavaScript. This kind of thing is 100% cool, in my opinion. People hear me, shit on JavaScript all the time. I don't. There's very valid use for it. It's when people use it to document their cargo crates and stop everybody from reading the documentation because they do so that I get mad. For reverse engineering, absolutely is a must. Yep. Is that reverse engineering a binary is like being given a person's DNA and trying to figure out? Yeah, absolutely. Absolutely. Yeah. Well, I think that's going to do it for me. Cheers. I still have Brandy left, which means it's fine. I'm going to go make sure I didn't leave anybody hanging, but I'm pretty sure. I mean, they knew I was streaming. I told them ahead of time. So I thought it was going to be 10 minutes and then this, and I feel bad, but I'll go figure what's up. Chapter 2 is ended. You've got chapter 2 under your belt, and now you've added pointers and memory to your toolbox. That's a big deal. I don't like that they call the next chapter 2.5. That makes me angry. Because I don't know why they do it, but all right. So we did scanf, we did ints, we did chart pointers, all this stuff. All these videos are on YouTube, by the way. I went ahead and I made a playlist. It's the second playlist from the top. The boost is still the first playlist. And so if you want to watch this on YouTube, you can do so. If you don't want to come suffer with us on Twitch, I did go 2 hours or so on this particular video. That is hopefully going to become an anomaly. I really need to isolate the amount of time that I spend here from my own health and for that of my family. So I'm going to be doing 9 to 10 tomorrow, but we'll be right back in here and we'll jump into 2.5 tomorrow. It gives you a breakdown of what elf starts. There's another one called Read Elf. Oh, GDB does it as well too, right? Maybe we'll get into that stuff tomorrow. Whatever XXD dump does. Yeah, Funkmain, we were kind of talking about that earlier. So if you'll be here for tomorrow, we can get into some of these more advanced tools for examining the elf binary, which I really want to do. This is the first time we've seen the breakdown of the binary and the running memory. So I appreciate that. All right, everybody. Bye-bye. Who should we raise Strager on? Channel. I mean, I'm going to turn the stream off these days, so I'll give Strager. Actually, let's give Nick. Let's give Nick a raid. I kind of go back and forth between the two. Yeah, let's do that. Tell him hi for me. Channel. Creator dashboard. I'm getting faster at this. See y'all. Wait, maybe not. Is he not on anymore? Oh, he's not. He's off. Oh no, he's not. He's done. Okay. Anyways, he was just kind of off the screen there. So say hi to our data science friend, machine learning / data science friend. I love that we have people on Twitch that know really amazing things that I don't know. So say hi. Bye.